One of the nice things about simple projectile motion is that the horizontal and vertical components, we'll talk about that, it's a physics term, of the motion are independent. So we can view the horizontal distance, velocity, and acceleration parts separately from the vertical counterparts, in which case we can have parametric equations for both of them. Now, this example that we're going to do here is a little bit of setup for Calculus 3. It's one of the earlier questions that you do in Calculus 3 also. So we're just kind of teach this to you, a little bit of physics, a little bit of Calculus 3, and also some Calculus 2 all at once. Won't that be exciting? So we have an airplane that's traveling at 80 meters per second over flat ground at an elevation of 3,000 meters. Some important points to notice there. And it releases a package with no propulsion and negligible air resistance. I'm not even going to speculate what this package may be. Okay, so let's think about this. Let's sketch a graph of the trajectory and think about the horizontal and vertical components, because this is a different way of thinking about motion, and it's the beginning of some other stuff. Maybe you've seen it in physics, but if you haven't taken physics class yet, this might be familiar or not, would not be familiar to you. All right, so I have a plane. It's a plane. It's a terrible plane. I recognize that. I'm not a good drawer. Okay, so we have our plane, and it's traveling this way. It's traveling this way over flat ground. That's why they're giving us flat ground. We're not even dealing with the curvature of the Earth at this point, although it is there, and you would have to deal with it in physics class when you get advanced enough. All right, so at this moment, it drops a package, and that package doesn't just fall straight to the ground. It has the motion of the plane to kind of nudge it along. So it goes like this, and it travels along that trajectory. Notice the arrows because it's a parametric curve. And then it impacts over here. So that's the point of impact. It hits the ground. Now it starts up here, and it's kind of up to us the way we want to think of this. So I think it's easiest if we make this start at 0, 3,000, which was t equals 0, right? So it's easiest if you make this the origin and then make this distance right here, 3,000 meters, if that's the origin. The other way to do it is to make the origin up at the top where the plane is. Both methods have their uses, but for our purposes, we'll make the origin down here. All right, now we created a parametric, we sketched a graph of the trajectory. Ta-da. We have the arrows showing that path. Very nice. We have our important numbers marked out. Lovely. We want to know, create parametric equations for the horizontal and vertical displacements, right? Displacement, i.e. distance, right? So we want to know the horizontal and the vertical at time t. No problem. And then we want to know the time since the package was dropped. All right, so let's see here. Horizontal is pretty easy because horizontal is just 80t. Right? 80 times t. That's it. It's because of the plane. So what's happening is that package has 80t. That's the x component of the package. And it's because of the plane. Right? That plane gives it to us. All right. So now, what about the vertical? Well, the vertical we've covered in Calculus 2, but you've also covered it in Calculus 1. All right, so we all know that vertical for a falling body, which is what the vertical component of this is negative 4.9 t squared plus v0t plus s0. Looks familiar? Yeah, we actually derived all of this back in chapter 6, so it was a long time ago. The 4.9 comes because gravity is negative 9.8 meters per second squared. Now, if we were working with feet, it'd be negative 32 feet per second, but we were working with meters per second, so it's negative 9.8. So again, see chapter 6. Right, we already learned that a long time ago. That's C, S-E-E, not S-E-A. All right, so let's think here. Our initial velocity in the downward direction, because that's what this is. So don't think 80. 80 is in the horizontal direction. The initial velocity in the downward direction is actually 0. So that means that y of t is actually negative 4.9 t squared plus 3,000. That was our S0. All right, so there we have it. There's the horizontal, there's the vertical, there's the horizontal. You didn't throw it downwards out of the plane. That's why V0 is 0. It's just dropped from the plane, right? So if it's just dropped from the plane, then it has an initial velocity of 0. That's what they're saying, it has no propulsion. Now, if it was propulsed downward, right, if it had a little engine on the back of it that was somehow pushing it downward, that would be a different story. But we don't have that. Now, the one thing we do need out of all of this, though, is we need to know when it stops, because that means that when we write a parametric equation, so if I write ADT, comma, I'm actually going to write it in color here. So if I write ADT, comma, negative 4.9 t squared plus 3,000, that's not a valid parametric equation unless I also give it limits. Well, obviously I can't go before time 0 because that's when the package was dropped out of the plane. But what I need to know is when does it impact? And since it doesn't have to be precise for this particular problem, I'm just going to use Desmos. This is what it is good for. So let me go grab this problem. All right, there it is. There's the ground down there. There's the package coming down. And we can pause it right around there. And we can see where the intersection is. As a matter of fact, I think to actually get the intersection, I actually have to do it that way. There we go. So that intersection happens, well, oh, it's when t would be equal to, or when the vertical component is equal to 0, right? Of course it is. So if you wanted to find this by hand, what you're doing is you're setting this equation equal to 0 and you're solving it, right? So what we really need is 3,000, negative 3,000 divided by 4.9, and then take the square root of it. So it just occurred to me right there that I'm doing it that way. All right, so let me see here. Let me grab, oh, I might have it in the calculation section. Nope, I'll just grab it. All right, so if I take negative 3,000 and I divide it by negative 4.9, which gets me that, and then I take the square root of that, because of course it was t squared, square root. It gets me 24.743. So this is when it hits the ground. So the point of impact, 24.744. I'll just say 24.74. Is t equals 24.74. And again, you find that by setting this equal to 0. Maybe I should do it in green. You set this equal to 0 and you solve for t. Subtract the 3,000, divide by the 4.9. You can also use Desmos, right? Either way. Now, the reason Desmos wasn't finding the answer for me right off the bat, of course, was because I'm just graphing the trajectory and the ground. That's not getting me time, right? So time I have to find a different way. So, but I can still use Desmos to do the calculations and such for me. All right, next I want to determine the coordinates of the final destination of the package. All right, so that impact time, which we just did, but I'll do it again. Again, would be negative 4.9 t squared plus 3,000 equals 0. So that would mean negative 4.9 t squared equals negative 3,000. In case you weren't following what I was doing before, t squared is negative 3,000 over negative 4.9. So when I take the square root of both sides, we get 24.74. Now, that's not the answer, right? That's just the time, right? Now, the coordinates would be, well, let's see here. That we could see. So the coordinates would be 80t, so that would be 80 times 24.74. Because that's the time when it impacts. And then the vertical, well, we know what the vertical will be. If we did this right, then when I substitute back in, I should get 0. Yes, indeed. So this should be, but I mean, I can write it. Negative 4.9 plus 3,000, right? And then I'm putting 24.74 in. This has to be 0. right? It has to be, because it's when we figured out it hits the ground. If it isn't 0, then you know you did something wrong. And this one was that other number that I was seeing. So if I go back to Desmos really quickly, I can see when I look at the algebraic equation right here. Oop, let me move that parameter off because I don't need that right there. I lost my ground. Oh, it's because I scrolled. Hold on one second. There we go. I made a few adjustments to make this work out. So you can see right there, 1979.487 and 0 because it's hitting the ground. I really had it negative 3,000, but that's because I wrote a slightly different equation, but it'll work. So at 1979.487, which of course I could also find in my calculation section if I just want to say x prime at impact, right? Or excuse me, x of impact, right? So that would be 80 times 24.7435829,653, and there you can see it. All right, so I'll write that down. So this is 1979. Now, what would this be? Well, x is in meters, right? Actually, I can put that after the whole thing because technically both of them are in meters. X and Y are horizontal and vertical distance displacement. So these are both in meters. So the coordinates of the package are right there. Now, if you want to give yourself more decimal places, that's fine. But notice that X and Y, it says it right here, they're vertical displacements, aka distance, right? Distance with direction, right? So these are both vertical and horizontal displacements, so they're distance, so they're measured in meters, as opposed to time here, which is in seconds, right there. So if you want, you could actually put up here on this one meters, because both of those components are meters. Now let's determine the impact velocity, all right? Now, impact velocity is not as easy as you might think. So impact velocity is a little bit tricky. So let's think about this just a little bit. So when it's coming in, it's moving downward, right? So we have a dy dt that's negative, right? It's going down. And then we have a dx dt, it's moving to the right, right? It's going this way, right? So that'll be positive. So this will be positive, this will be negative. Moving downward is negative, moving to the right is positive. Now, the impact velocity is not just the ratio of the two. No. There's actually, your impact is coming along like this, and we'll call that z, right? So the impact velocity is dz dt. Now, I know what you're thinking. Well, how would I find that, right? I wasn't given a z. But you know x and you know y. So, and look at what kind of object we have drawn. Pythagorean identity, right? So dx dt squared plus dy dt squared will be equal to dz dt squared. Okay. So dx dt, okay, well, that's the derivative of x. So the derivative of this with respect to t is 80. So this will be 80 squared plus the derivative of this would be, well, the acceleration due to gravity, which is negative 9.8 t. So negative 9.8 t, and we're going to square that, which would be equal to dz dt squared. All right, well, this is what I'm looking for. So I've got it. The only thing is that I need to put in my impact, right? So at the point of impact means we're going to substitute, will mean we're going to substitute t equals 24.74. So I'm going to plug in that value right there. I'm just going to star this. Right? So right there, we're going to plug in a value, right? This value. So I'm going to take 80 squared plus this number squared, right? And I'll get, let's see, 80 squared, which I know, but, I'll leave it alone, right? 64,000, right? So, I mean, I guess I could write that. 6,400. I mean, give me 1 second. Just looking for a pen. 64, because 8 times 8 is 64. And then 0, 0 makes 6,400. All right, then I need to take negative 9.8 times 24.74 and square that number. So I'm just going to make Desmos do that. So it's right here in my calculations. So 80 times 24.74. Oh, that was the earlier problem. Sorry. Let's see. There it is. Negative 9.8 times 24.74 is 242 point blah, blah, blah squared. And then when I add them both together, the 80 squared plus the 242.487 squared, I get 65,199. Okay. So this one right here was, I'll just write it this way, negative 242.452. And then we're squaring that number. All right, together these numbers made 65199, right, when I got them out of Desmos. Yeah, 65199.945. And again, this is equal to dz dt squared. So dz dt would be equal to the square root of these values, or this value. So dz dt, which is the impact velocity, would be equal to the square root of 65199.945, which is, according to Desmos, 255.34. 255.34. Let's leave it at that. Now, it's an impact velocity, so its unit must be meters per second. It's a velocity. Distance divided by time. And if you're thinking, oh, this seems a little bit interesting, yes, that's the beginning of vector calculus for Calculus 3. So we'll deal with these in terms of vectors in that particular course, but it's the same concept and same ideas. So, recapping, we found the trajectory based on two components, x of t and y of t. Y of t in particular is based off formulas we already know from earlier in calculus. Then we're able to find the time and impact. Then we're able to use that time and impact to find the final destination, the placement of impact, where it hits. And then using some craftiness, we're able to find out how fast it hits, right? What the impact velocity